In this lecture, we will discuss Index of Hydrogen Deficiency, which is also known as Degree of Unsaturation. It is defined as half the number of hydrogens missing from the molecule, compared to an analogous completely saturated molecule, whose general formula is CnH2n plus 2. Before going into details of Index of Hydrogen Deficiency, we will understand this general formula for saturated alkane. Take for example a 1-carbon saturated molecule. Based on tetravalency of carbon, it is attached with 4 hydrogens and is called methane. We will encircle these 2 hydrogens and put these 2 in red rectangle. Compare it with a 2-carbon alkane. It is called ethane. It has 2 hydrogens encircled at the end just like methane. And each carbon is attached to 2 hydrogens, shown in red rectangle. In the 3-carbon alkane, notice the same pattern, it has 2 hydrogens at end which are encircled. And each carbon is attached to 2 hydrogens as shown in red rectangle. This pattern is common to higher homologues. Thus the general structure for saturated alkane can be written as H, CH2 times N, H. It means in any saturated molecule, each carbon is attached to 2 hydrogens plus those 2 hydrogens at the end. Thus the general formula can be written as Cn, H2n, plus 2. This is true even for compounds that are branched rather than having a straight chain. For example, all these structures have same molecular formula C5H12. These compounds are said to be saturated, because they possess the maximum number of hydrogen atoms possible, relative to the number of carbon atoms present as per the saturated formula Cn, H2n, plus 2. If we put a double bond between 2 end carbon atoms, we get this structure, with molecular formula C5H10. If we put a triple bond between 2 end carbons, we get this structure, with molecular formula C5H8. In other words, we can say, this double bonded structure has 2 hydrogens less than the saturated molecule. And, this triple bonded compound is obtained by loss of 2 more hydrogens. Thus, a compound with a pi bond, be it double or triple bond, will have fewer than the maximum number of hydrogen atoms. Such compounds are said to be unsaturated. Thus, the degree of unsaturation in this double bonded structure is 1, and for this triple bonded structure it is 2. A compound containing a ring will also have fewer than the maximum number of hydrogen atoms, just like a compound with a double bond. For example, if we join the end carbons in this 5-carbon saturated structure, we get 5-membered cyclic structure, with a molecular formula C5H10. Thus, this structure has 2 hydrogens less than the saturated molecular formula of C5H12, hence amounting to index of hydrogen deficiency of 1. We can now say that, each double bond contributes 1 to molecules IHD. Each triple bond contributes 2 to molecules IHD. And each ring contributes 1 to molecules IHD. With this in mind, let's explore how to calculate the IHD, when elements other than C and H are present in the molecular formula. Take halogens first, compare the following 2 compounds. Notice that chlorine takes the place of a hydrogen atom. Therefore, for purposes of calculating the IHD, count halogen as if it was a hydrogen atom. In other words, C2H5Cl should have the same IHD as C2H6. In case of oxygen, compare the following 2 compounds. We have inserted oxygen between carbon and hydrogen to form ethanol from ethane. Notice that the presence of the oxygen atom does not affect the expected number of hydrogen atoms. In other words, C2H6O should have the same IHD as C2H6. Even if we insert oxygen in between 2 carbons to form an ether molecule, the number of hydrogens is still not changed. Therefore, whenever an oxygen atom appears in the molecular formula, it should be ignored for purposes of calculating the IHD. In case of nitrogen, a nitrogen atom can take the place of a carbon atom in the chain, but nitrogen is trivalent, having only one additional hydrogen atom, compared with 2 hydrogens for each additional carbon atom. Thus, in computing the elements of unsaturation, count nitrogen as half a carbon atom. These rules will enable you to determine the IHD for most simple compounds. Alternatively, the following formula can be used: IHD equals half of twice carbons, plus 2, plus nitrogen, minus hydrogen, minus halogen. Consider this molecule. It is called propane with molecular formula C3H8, it is saturated. If you take the same number of carbon atoms with a double bond between 2 carbons, it is called propene with a molecular formula C3H6. Since it has 2 hydrogens less than saturated propane, the index of hydrogen deficiency is 1. Thus we can say propene is formed from propane by removing 2 hydrogens. Alternatively, if the 3 carbons form a ring structure, it is called cyclopropane. With molecular formula C3H6. Again we can say, IHD equals 1. Because it has 2 hydrogens less than saturated propane structure. If we put a triple bond between 2 carbons in this 3-carbon molecule, it is called propyne, with a molecular formula C3H4. The IHD equals 2. Because it has 4 hydrogens less than saturated propane. Alternatively, it can be said that propyne is formed from propene by removing 2 hydrogens. Similarly, this molecule has molecular formula C2H6 and is saturated. If we add oxygen in between 2 carbons to form ether, with molecular formula C2H6O, it is still saturated, as number of hydrogens remains same. Alternatively, if we insert oxygen in CH bond, to form this alcohol molecule, with molecular formula C2H6O, it is still saturated. From this alcohol molecule, if we remove 2 hydrogens, so as to form a pi bond between the carbon and oxygen, we get this aldehyde molecule, with a molecular formula C2H4O. This has 2 hydrogens less than saturated C2H6 ethane molecule. Hence IHD is equal to 1. Another way is, if we remove 2 hydrogens from this ethanol molecule, to form an epoxide ring. The molecular formula becomes C2H4O, which amounts to IHD of 1, as there are 2 hydrogens less than saturated C2H6 formula. We can now say that, these 2 structures have 2 double bonds each, hence IHD for each structure is 2. These 2 structures have 1 triple bond each, hence IHD for each structure is 2. This structure has 2 rings, hence IHD is equal to 2. These structures have 1 ring and 1 double bond, hence IHD for each structure is 2. This branched alkane is saturated as it has no unsaturation or ring in it. This similar structure has 1 double bond, hence IHD is equal to 1. This has 1 ring and 1 triple bond, hence IHD is equal to 3. This pyridine molecule has 1 ring and 3 double bonds, hence IHD is equal to 4. This structure has 1 ring, and hence IHD is equal to 1. Notice that fluorine takes the place of hydrogen and hence doesn't affect the IHD. This structure has 2 double bonds and 2 rings, hence IHD is equal to 4. This structure has 3 double bonds and 2 rings, hence IHD is equal to 5. This structure has 2 triple bonds and 1 double bond, hence IHD is equal to 5. Let us now try calculating IHD for given molecular formulas. Take C4H4Cl2, IHD equals half of 2 times 4 carbons, plus 2, minus 4 hydrogens, minus 2 chlorines. This equals half of 10 minus 6, which is 4, divide by 2, equals 2. For C4H8O, IHD equals half of 2 times 4C, plus 2, minus 8 hydrogens. Which gives IHD equals 1. For C6H8O2, IHD equals half of 2 times 6C plus 2 minus 8H, which comes to 3. For C5H5NO2, IHD equals half of 2 times 5C plus 2 plus 1N minus 5H. This comes to 4. For C6H3NClBr, IHD equals half of 2 times 6C plus 2 plus 1N minus 3H minus 1 chlorine minus 1 bromine, which becomes 5. For C4Cl6, IHD equals half of 2 times 4C plus 2 minus 6 chlorine, which becomes 2. For C100, H200, Cl2O16, IHD equals half of 2 times 100C plus 2 minus 200H minus 2 chlorine, which comes to 0, thus this is saturated.